I'm here with Professor Paul Skrzypczyk, who works at the University of Bristol. Paul, what does a normal research day look like for you?
Uh, so that's a good question. So nowadays it's a bit different than it used to be when I was a PhD student. But like for me now, as a permanent academic staff, lots of my research is actually with like colleagues and students and collaborators. So a typical day might be, coming in and doing the boring stuff. But then when I get to the fun bits, would be meeting with my PhD student for 1 or 2 hours. Then they'll give us an update on me, or like if it's with colleagues, like on what they've been working on, and we'll kind of talk through their progress for the week, what ideas they've had, maybe what they've been stuck on. If we're writing a paper, we might talk about the drafting of the paper, like the ideas, you know, brainstorming a bit and taking it from there. So that's the main way in which I get to do like lots of my research now, is actually kind of vicariously through students. Also, I have like undergraduate project supervision, so final year project students at Bristol, and we always do kind of research questions with them. So this can also be lots of fun, especially this time of year when we're kind of at the end of the project and they've learned lots and now they're really doing exciting things. So have a two pairs of students this year who are all making great progress on a couple of theoretical projects.
Mm.
But this is the reality, I would say, for most academics nowadays, is that it's not that I get to sit down and do the kind of calculations I'd love to be doing myself, but I get to kind of do them in collaboration with my students.
Mhm.
Yeah.
So you must come into contact with a lot of different ideas that you would like to follow if you had infinite time. So how do you choose when an idea is worth pursuing, and how do you choose when to kind of kill your babies?
Yeah, that is a difficult one. I guess I tend not to try and kill ones. I tend to try and kind of keep them in the mix for as long as possible until maybe they fall off the bottom of the list. This bit feels very unscientific to me. I don't have a master plan that kind of comes about where you say, okay, this has to be the thing I work on. I guess when you find an idea, you tend to know in your gut if this is like really the one that you want to like devote your time to, or if you pull at the thread a little bit and then you might realize that this all seems to be falling into place.
Mhm.
Sometimes you read a paper and you're like, oh, actually they've done this thing and I think I could do this and this is really important. So I guess the more experience you get, the more the better you get at kind of judging ideas very quickly, to be like, oh, actually this feels like the right idea, or this doesn't. But the truth is, I guess this is what to some extent differentiates the very successful academics from the not so successful ones, is the ones who really know, like, have that innate ability to kind of see the good questions and
Mhm.
attack them head on, rather than like maybe spending most of your time working on the ones which in hindsight you're like, oh, actually I could have worked on something else at that time. So
Mhm.
I don't. Yeah, it's a really difficult question to answer. It's a really nice question. I don't know if someone has a better answer than me. I'd love to know it, but it
Put it in the
typically,
comments, guys.
yeah,
Yeah, yeah.
what I find is that it's a bit of a random walk, and it's mostly kind of following your gut, like
Mhm.
what gets you, and what is it that thing that you find yourself thinking about. For me, is typically the thing I really want to work on, because
Mhm.
then I know I'm going to put the effort in
Mhm.
more than the other projects. Right? Like there's a bit of a competition of ideas,
Mhm.
and you pick the thing that is currently you can't get rid of out of your mind.
Mhm.
Um,
So it's easy to imagine what progress looks like for an experimentalist,
mm.
putting out papers and getting data. What does progress look like in theoretical physics?
Yeah, it is very different, I guess, in that it is still highly nonlinear. So there will be these kind of moments when maybe you have like a huge amount of progress, and then you might feel like you're kind of stuck for a long time, trying to kind of figure out what is the correct way of solving the issue. So it can often, there's a few different types of problems you encounter. Sometimes you know exactly what you want to calculate, but you just don't know what the correct way to do it is, or you have the feeling that there's some, if you can prove some relationship mathematical between some quantities, that maybe that will be enough to then kind of have a next consequence, and you kind of follow that. And so you kind of, a lot of it is like breaking down your problem from like where you think you would like to get to into kind of smaller steps, and then seeing how might you do those kind of step by step. Sometimes, as I said, it's really like a mathematical issue in that you know exactly what needs to be shown. It's just it's not clear like what the mathematical tool is to do it. And nowadays, you might go and ask a model what it thinks is a good idea, or you might Google, you might talk to people, you read papers. So always, in that sense, I'm always kind of looking out for techniques and tools, which I guess maybe is a little, probably there are analogies in experimental discipline, which I'm not aware of, but I guess it's a similar thing. Like you're trying to achieve something in the lab, and you kind of need to know that it's achievable
Mm-hmm.
and the right way to build it, or to get that kind of precision you need, for example. Other times the problem can be conceptual, and actually a lot of the time it's just arguing out what actually is the right question.
Mm-hmm.
Like a lot of the things I work on, often the question we start out trying to study is not the question we end up answering, either because we couldn't answer it or just because we were slightly wrong in the question. And the real it takes 9/10 of the time just to get to the question, which is actually the one where you're like, oh, I see, that was actually what I should have thought about before.
Mm-hmm.
And sometimes you're just confused. Yeah, I guess it's like you're just there a bit in the dark, stumbling around, trying to make progress. So I guess this is the main thing. And in my case, lots of my work is analytical, like on pen and paper or on the blackboard. Um, but often, and like it's over the years, it's changed a bit, but finding ways of like using the computer to kind of help you has been a big thing for me. So sometimes just understanding, oh, how could I transform this into a way that the computer can then give me a solution, and then maybe once you've got a solution, then you try to turn that back into something analytical
Mm-hmm.
that you can then kind of play with. So this is a big part of the problem. Often, I would say,
Mm-hmm.
yeah.
Great. And if you were to look back at your career so far,
Mhm.
what is something that sticks out as something you're particularly proud of?
Uh, okay, let me have a think. Yeah, I guess there's a couple. One that I guess for me is particularly proud, just because it was a huge aha moment. Was we were looking at uh, quantum teleportation, which is the ability to kind of transfer the state of a particle from one place to another. And actually, a colleague of mine, he'd been asked a nice question at a conference. So he was at a conference, and experimentalists came to him, and he'd done a nice experiment on teleportation, and he kind of asked what I think he thought was a pretty innocent question to my collaborator Danny, which was, "Oh, how does this relate to this other effect steering that Danny and I had thought a lot about? So it's another type of non-locality." And that we were kind of had spent a lot of we were kind of building up our expertise in this direction, and this experimentalist Paul Quiet, he kind of asked Danny, what's the relationship, I think assuming there'll be a very quick like answer. And I guess Danny couldn't answer, and then he came back and we were discussing, and then we thought, oh, it will be easy, and then we couldn't answer it, and it took us an amazingly long time until we finally kind of understood the right way to look at the problem. So we were just looking at everything from the wrong direction, or
Mm-hmm.
there was one ingredient that we just didn't see. And so finally, when we had the final idea, and I was visiting Barcelona, and I was about to leave, I had like an hour to go or something like this, and we were sat at a cafe, and then finally the penny dropped, and we were like, oh god, like that is that's the answer. And it was just so blindingly obvious after the fact that we could have kicked ourselves for having how long we spent kind of going round and round in circles. And so for me, this sticks out because it was nice. And then we went through that whole phase where you're like, okay, if it was this obvious to us in hindsight, then probably someone else knew this.
Mm-hmm.
And so then we were trying to do our kind of diligence to make sure that, could we find other instances where someone had made this connection? And we kind of came to the conclusion that no,
Mm-hmm.
that wasn't done. And so we wrote this up, and and the nice thing is that once we saw this connection, so once we understood this formal connection between these two phenomena, um, then it immediately allowed us to basically import all of the like mathematical framework that we'd been developing for steering. We had a certain way of thinking about it, like in a geometrical nature, and that allowed us then to import all of this into the way we were thinking about teleportation, which
Mm-hmm.
for us was really powerful. And then this led to kind of lots of follow-up work. So this for me, I was kind of proud because it was two important topics, and seeing this connection between the pair of them in this nice way, I think was something that it was nice to achieve. And it was I'm still proud of it even to today,
That's
basically.
fantastic. One last question. Um, I know you teach undergraduates as
Mm-hmm.
well as being an active researcher.
Yes.
Do you have any advice or resources that you would recommend for people watching who might just be getting into physics or thinking about a university education?
Also, like incoming undergraduate
Mm-hmm.
students. Yeah, so I guess there is lots of advice one could give. The mate, I mean, one of the big ones is learning to persevere, learning to like spend that time trying to solve that problem. It isn't going to be misplaced effort. So university degree, every year of your degree is going to be harder than the year before. But by the end of that year, you should hopefully be able to look back and be like, oh, actually, I can solve things. My understanding, my physical intuition is better than it was before, and that won't come without putting in the hours, unfortunately. But there is this real difference between like cracking your head against a problem and really staring at it and not getting the answer straight away, but saying, okay, I need to take 5 minutes, I need to go and have a break, I need to come back and then think about it again. And if you solve it yourself, that one time, and you really did it and you understood how you got there, then the next time it will be much easier. And this kind of learning journey is like, kind of, you see something the first time, you're a bit shaky, you then try to solve problems on it. The problems won't necessarily come naturally, but you want to kind of see that progression. I think this is the biggest thing, is kind of learning how to kind of solve problems, and also reflect on how you learn as well, right? When you come into university, the way you've learned at A level is not going to potentially be, well, probably almost certainly won't be the way you want to learn by the time you finish university. And actually being a bit mindful about what works and what doesn't work and how you can actually approach your own learning, I think is really important. And I think it's something we don't tend to do. Historically, it was always assumed that everyone just would learn, just knew how to learn. And then you might not get taught how to learn, but actually thinking a little bit about how do you learn is really important. So I'm a big advocate of a certain teaching style called flipped learning, where I provide videos to students to watch in their own time. And then that means that when I do meet with students, I can be kind of more active in my teaching. And some students struggle with this teaching style, which is understandable because it's kind of unfamiliar, and they actually have to learn how to learn from flipped learning approaches, right? They need to kind of learn to be able to take those videos and concentrate and watch them, or pause and stop and think. But once they've kind of mastered this as a learning technique, then it can be really powerful for them. And so you shouldn't be scared about kind of like, oh, I come along and it doesn't work immediately. Sometimes you just need to give yourself a bit of patience, a bit of time, and patience will actually show that you can kind of learn to appreciate the power of something which maybe at first sight isn't quite so obvious.
Brilliant. Thank you, Professor Paul Skrzypczyk.
Thank you very much.